Good morning, everyone, and thank you for joining us for this training session on the regionalisation of ocean climate indicators. So I'm Samantha Hallam, so I'm a senior postdoc at Maynooth University here in Ireland. I'm a physical oceanographer with a particular interest in air-sea interactions, so particularly storms, so looking at storms in the tropical Atlantic, but also extratropical storms in the Gulf Stream region and how the Gulf Stream influences that. And as part of OBSE for CLIM, the work that I'm undertaking is really around the regionalisation of ocean climate indicators. So this training session will be in two parts. I'll do around 20 minutes and then I guess there'll be questions, and then Oren will cover the second slot this morning as well. So in terms of what we're going to cover, we're going to introduce the concept of ocean climate indicators, discuss their relevance and usefulness and the role they play in the policy nexus. And in the context of OBSE for CLIM, we're going to be focusing on the physical ocean indicators for climate. So obviously OBSE for CLIM is all about ocean observations and indicators for climate and assessments. So that's our area of focus. And the training session will cover the following areas. So why do we need regionalisation of ocean indicators and what approaches can be adopted? That area will predominantly be covered by myself, and then Aurélien will come into how to use multi-product data sets, accounting for uncertainties and method sensitivity to enable regionalisation of ocean indicators. And both of us will cover examples of regionalisation and the variability observed. So just going back for a moment as to what all this is about. So one of the key objectives under OBSE for CLIM is to develop and deliver new ocean indicators for sustainable development to provide improved essential ocean variables and essential climate variables to evolve the European ocean observing. So that is really where the whole of this work sits. So why do we need ocean indicators? I think this is a very interesting slide from WMO on the state of the climate. And basically what it says is that 5 of the 7 WMO state of the climate indicators are actually ocean indicators. So it highlights the importance of the ocean for climate. So what we have there is ocean surface temperature, ocean heat, ocean acidification, sea level, and Arctic and Antarctic sea ice extent. And in terms of OBSE for CLIM, we're looking at 4 of those, so surface temperature, ocean heat, sea level, and Arctic and Antarctic sea ice extent. Ocean acidification, as I'll come on to, is looked at by a sister project. So what are ocean indicators? So there is a very nice paper on global ocean indicators, which has been led by Karina von Schuckmann, which has recently been published in the Journal of Marine Policy. And obviously Karina is part of OBSE for CLIM, leading the overall task on ocean indicators. Basically, it's saying that they are measures of scientifically verified approaches that identify the state of the ocean across a range of temporal and spatial scales, and they're accessible to informed decision makers and beyond. So these are the 6 criteria for a robust ocean indicator. So they need to be verified. So what we mean by verified is it needs to be peer reviewed, and so it has a scientific rationale as to why it's an indicator. It also needs to be significant, so important enough to provide important information about the ocean phenomena that it's talking about. It also needs to be scalable, and this can be where some of the issues occur. So scalable both temporally and spatially. So obviously one of the challenges spatially is taking something from a global all the way down to a very small scale coastal level, for example. And also temporally, that can also form issues that obviously in terms of temporal data, in terms of satellite data, that only goes back to the 1980s. So prior to that, data can be more sporadic in nature. It also needs to be justified. So it needs to have be able to inform a decision making and be understandable by a broad audience, so outside of the scientific community, and also measurable in terms of an EOV and essential climate variables. And finally, it needs to be accessible, so in terms of the fair and care principles for data. And the link to the article is in the QR code, and I think Justina will share the paper afterwards as well. And this is a nice slide, I think, in terms of also from the paper that's just been published, which shows how everything links together as part of the overall ocean knowledge transfer. So at the bottom, we have our essential ocean variables and essential climate variables. That then links into the ocean indicators, and then in terms of the reporting and assessments and the ocean narrative. So what does this tell us about the economy, and what does this tell us about society and the environment, and how can that then help inform policy overall? So out of the paper, there have been identified 9 pilot ocean indicators. So, and they come under 3 sort of broad areas. So the ones which we're looking at in OBSI for CLIM are the physics and climate, as I was saying earlier, so the ocean warming, sea level change and sea ice change. Then we have the biogeochemistry, so we've got there the ocean acidification, ocean deoxygenation and net community production, and that's been looked after by the sister project of BioGeoC. And then finally, we have the biology and ecosystems of seagrass cover and change, phytoplankton composition and concentration change, macroalgae, canopy cover and composition change, which is being looked after again by the sister project BioEco-Ocean. So why do we need the regionalisation of ocean indicators? Well, the key reason is that obviously we have very unique patterns in different regions, and it's interesting to compare the regional trends to the overall global trends. Often we talk about the global trends, but people are interested in what's happening in their local region. And that then enables us to isolate the mechanisms and drivers behind the differences that we're observing, and that helps to inform stakeholders so that they can develop policies to address local challenges. However, it's not as simple as that, because some of the ocean indicators may have a local but also a remote influence. So we need to try and tailor the ocean indicator to the question that we're trying to answer. So, for example, if we take a slowdown in the AMOC, so the Atlantic Meridional Overturning Circulation, so if we have a slowdown in the AMOC, we believe that that's associated with the warming hole that we're observing in the subpolar jar region in the Atlantic. That evidence suggests, and some scientific papers, that a slowdown in the AMOC can lead to blocking and changes in the jet stream patterns leading to blocking, and that can then alter European weather and potentially cause heat waves over Europe. So that's an example of how you have a remote indicator over the North Atlantic which is influencing European weather. And similarly, you can get a warmer North Atlantic, which again can cause changes in European weather, and melting Arctic sea ice, where we can see that that's causing changes to the atmospheric circulation and more extreme weather. So that leads us to the question that we might need a local or a remote ocean indicator, depending on the question that we're actually trying to answer. So, for example, here in Ireland, one of the questions that we were asking is, why is mussel condition changing around Ireland? And what we identified was that local Irish sea changes in sea surface temperature was actually was potentially a good indicator of that. Similarly, we could be asking, why are air temperatures in Lithuania rising faster than some other countries? And again, that could be associated with changes in Arctic sea ice and North Atlantic Ocean temperatures, again influencing the atmospheric circulation and the jet stream patterns, leading to warmer than average temperatures over Lithuania. So how did we go about agreeing the regions that we wanted to do for this regionalisation? So first of all, we took the essential ocean variables to be analysed, so sea surface temperature, sea surface height, sea ice and subsurface temperature. Then we put together the proposed indicators to measure the ocean variable, and then we put together the proposed region. So starting at the global level, then coming down to a regional level, then looking at the seas, then looking at case studies, and also looking at thematic regions. So what that looks like in practice, so here we have, for example, ocean temperature. And so there are 6 indicators which are being looked at. We've got mean sea surface temperature, ocean heat content, subsurface temperature, ice surface temperature, melt days, and freezing degree days. And so there's some very interesting work going on at the moment looking at ice surface temperature and how new data sets there can actually improve the proxy for under ice sea surface temperature to help improve what we understand to be ocean temperature overall. In terms of sea ice, we actually have 9 indicators, so sea ice concentration, sea ice extent, sea ice drift, thickness, age, area, freezing date, breakup date, and sea ice volume, and open water days. So the work that's being undertaken is looking at each of those indicators, establishing what data is available, the uncertainty in all of those data sets, and to what extent it can provide a good indication of sea ice. And finally, we have sea level, and the 3 indicators there are mean sea level, in situ tide gauge data, and mass component of sea level. And here is a summary of the areas that are being looked at. So what we have here, we have the whole of the North Atlantic is one area. Then we have the Northeast Atlantic and the adjacent seas. Then we have the subseas, so we've got the Barents Sea, the Nordic Sea, the Baltic Sea, the IBI area, Mediterranean and Black Sea. There's also the local marine ecosystems, which are similar to the seas, but slightly different on the west coast. We're also looking at case studies around Ireland, so the EEZs around Ireland and Finland. And for the sea ice, we're looking at the Arctic and the Antarctic. And then we have 2 thematic regions as well. So we're looking at the Gulf Stream region, which is the box here in blue, and the main development region for hurricanes down in the Northeast Atlantic too. So just wanted to share with you now some work that's been done on the regionalisation of SST around Ireland. So this is work being undertaken at Maynooth by Catherine O'Byrne, who's a postdoc here. And this shows you, first of all, in more detail, the Northeast Atlantic and the regional seas. So this is the first area of the comparison. Then it's comparing the satellite data for the Northeast Atlantic and adjacent seas with the blue line area, which is the EEZ around Ireland. And then we're looking at the green area, which is the 12 nautical miles. And all of that done is with OISST, which is satellite data. Then we're also looking at the in situ data. So then we're looking at the buoy data. So we've got the pink and the blue dots for the buoys around Ireland, which is shown again here. And then we're looking at the coastal sites from an in situ basis as well. So combining all the coastal sites around Ireland. So we've got the Irish Lights, and then we have the OPW sites around Ireland, and then combining all of those together to give us an overall feel of the coastal sites. And one of the coastal sites is called Malin Head, and at Malin Head there's a very interesting record, because it's the longest available record for Ireland that goes back all the way to 1954. And so when we compare all of the data on a regional basis, this is the result that we get. So these are the decadal trends since 1982 for each of these areas. So the widest area was the Northeast Atlantic and the adjacent seas. So that's where we're seeing an increase over the period of 0.26 degrees per decade. Then we're looking at the EEZ, and for the EEZ, we're seeing a slightly lower trend around the Irish EEZ of 0.17 degrees per decade. For the 12 nautical miles, what we're seeing is it seems more similar actually to the Northeast Atlantic and the adjacent seas. For the in situ data, so this is the coastal regions and the buoy data. What we find is we're seeing something more akin to the Irish EEZ with a trend of 0.17 degrees per decade. So this is a combination of the buoy data and all of the coastal sites. When we look at Malin Head for the period since 1982, what we see is a trend, again, potentially more akin to the Northeast Atlantic, and the adjacent seas of 0.27 degrees per decade. What we also looked at was the Irish air temperature, and what that was showing was an increase of 0.24 degrees per decade. So it's interesting to then sort of think about this and try and reconcile what it's actually trying to tell us. And so obviously one of the things we were thinking is, you know, when we get closer to the coast, we're looking at Malin Head. It seems very interesting that that record is very akin to the surface air temperature around Ireland. So what we're wondering at the moment is the Malin Head record a true record of the ocean, or is it more influenced by the air temperature around Ireland? Which I guess is one of the things you need to think about when you're adopting this regionalisation approach. Similarly, with the 12 nautical miles, I mean, this is satellite data, and at the moment we've been using the OISST data set, which is got a 1/4 degree resolution. So potentially, it could be that some of the information in here could be influenced by overland. So what will be interesting is Catherine is currently undertaking looking at analysing this again with the Ostia data, which has got a 6 kilometre resolution. And it'd be interesting to see whether this 0.23 degree trend still continues once that analysis has been done, or whether we find something more akin to the EEZ. So in terms of, this is where we are currently in terms of looking at the regional variability in SST around Ireland, and we can see that potentially, if we look at the coastal data and the EEZ, that we have a rate which seems to be slightly less than what we're seeing for the Northeast Atlantic overall. But obviously one of the questions is still remaining, you know, is that within the context of the overall uncertainty and variability, or is that a distinct trend that we're observing, so that we're seeing something slightly different in around Ireland compared to the wider Northeast Atlantic? And is that potentially associated with the warming hole, or is it more associated with the fact that the Mediterranean seas are included in that area, which may be warming at a faster rate, which Aurélien will come on to. And then the second area that I just wanted to show you is something quite different. So as I mentioned earlier, we talked about a thematic region of looking at the main development hurricane region in the North Atlantic. And what we're looking at there is how we can use subsurface ocean temperatures as an indicator in the prediction of hurricane intensity. So what we have on the left-hand side here is the Caribbean upper ocean temperatures since 1980 for August, September and October. And what we find at the surface, we see a warming trend of 0.19 degrees per decade, but subsurface we find a lower increase over that period. And what we have here on the right-hand side is the intensity of Caribbean tropical cyclones since 1965. And MSW stands for the maximum sustained wind, so the strength of the hurricane, and MSLP stands for the minimum central pressure of the hurricane itself. And what we find in this work is that we have the best correlation with the minimum central pressure of the storm with the temperature over the top 100-meter layer. So that by using the average temperature over the top 100-meter layer, we can use that in terms of assisting us with the prediction of hurricane intensity. So we've developed a model on the back of this called the TOPIM model, which stands for Tropical Cyclone Ocean Coupled Potential Intensity Model, which uses subsurface Argo floats and atmospheric radiosonde data for potential intensity prediction. And so by using as an indicator, the temperature over the top 100-meter layer, as opposed to SST, we find that it actually improves hurricane prediction by 20 to 30 millibars on average. So here is some outputs from the 2 Category 5 hurricanes that have hit the Caribbean in the last 2 years. So Hurricane Beryl in 2024, the maximum sustained wind prediction was 135 knots, which was close to the actual, which was a Category 5 storm. And then Hurricane Melissa was 162 knots, and it provided that prediction over 7 days in advance. And that was basically within one knot of the maximum sustained wind that hit Jamaica in October 2025. And what we can do with TOPIM as well is we can keep the atmosphere the same and put it in different ocean conditions. So we know that, for example, with Hurricane Melissa, the ocean was 1.4 degrees warmer than climatology when Hurricane Melissa hit Jamaica in October. So if we put the same hurricane in a 1.4 degree cooler ocean, we find that it would have been a 126 knot storm, so a Category 4 as opposed to a Category 5 that was observed. So this is another example of how we can use ocean indicators on a prediction basis, which is obviously important for disaster preparedness. So thank you so much for listening to me. Hopefully I've given you a whistle-top tour around regionalisation of ocean indicators, and Aurélien in a few moments will go through in a bit more detail about how you can put the data together. So thank you for listening.
Hi everybody, so my name is Aurélien Linet. I'm working at Mercator Océan International, and I'm part of the Oxford program. I'm a climate scientist with a background in more internal variability and its role in the European climate. But now I'm focusing more in the ocean and in the regionalization of ocean climate indicators. So first, why do we regionalize ocean climate indicators? So this has been well described by Sam a few minutes ago. So I'll pass really quickly on this slide. But yeah, the main part is that you have unique patterns in different regions, and you might want to understand the drivers and mechanisms in these regions. You might want to compare it to global trends. And the main point that interests us in the end is to provide stakeholders with data to develop policies to address local changes. So yeah, this has been well described by Sam, so I will not go back to it. But the other point I wanted to focus a bit on this slide is that the question you're going to ask is really important, and this will guide you choosing what ocean climate indicator you want to regionalize. But we'll go in further detail later. So in this presentation, I will talk about how to regionalize the ocean climate indicators, and I will describe 5 steps that one should follow in this process. So first, defining the context. The second one is look for data availability, then check that the data you found are robust. And then you will process the data according to your context and analyze and interpret the outcome. And in order to illustrate this method or these steps, I will show a case study in the Northeastern Atlantic and adjacencies. And this is taken from the last Ocean State Report that was published this year. And so, yeah, each step will be illustrated with this example. So the very first step of the regionalization of ocean climate indicators should be the definition of the context. And so you want to find a question to answer. So we all know that it's quite difficult sometimes to find the question, but this question will really help us to find what we need. Especially we want to find which variables, so which ocean climate indicators we need, which one are relevant or not for the study. Then we need to find which region exactly we want to look at. And sometimes we want to look at single points. So this is something that was shown by Sam earlier, that there are some points on the map, and you might want to look at what's happening in a really particular region, or you might want to look at something that is area average, so a larger region. But sometimes also you might want to look at some maps to see the spatial patterns of changes. And then the third point is that you want to know what is your time scales and how far in past do you need your data to go. And this we'll see can have also a good importance in your study. And one important last thing about this defining the context is that you will need to do a lot of literature. So I think we are all aware of this, because some people might have done the same kind of study, but in another region, or studied the same region, but for other purposes. And this will guide us to find, to define the region, or to know what we should be looking at exactly. And so, for example, in the case study from the last OSR, the question is how fast did the Northeastern Atlantic and adjacencies warm over the last 40 years in the context of global ocean warming? So this is kind of an academic question. This is not really policy related as it is, but we'll follow this example today. So first, the variables. So I need the sea surface temperature in the Northeastern Atlantic and adjacent seas, and also in the global ocean, as I want to compare what is happening in the North Atlantic to what is happening at the global scale. For the region, then I need a definition of what is the Northeastern Atlantic and adjacent seas. This time I won't be using single point data. I won't be looking at spatial data. What I will need is some area average indicators. So if my data are not really refined in spatial resolution, it's fine for this case study. And for the timescales, so I need data over the last 40 years, but I don't need to have daily data. If I have monthly data or yearly data, it's fine for my study. So here's an example of how to define the context of the study. Okay, so now that I have defined the context, I can start looking for data availability. And in order to best understand what is happening in my context, I try to use all capacities available, which means possibly multiple data sets. And the idea behind this is that I want to be sure that the different data sets are agreeing in the signals that I show, because otherwise it would mean that it is not a robust signal. So there are many kinds of data that we can use. So in situ data, so for example, Argo in the oceans, or buoy data, satellite observations that are often covering a large or all the surface of the globe, but don't go as far in time in the past. Then we have reanalysis. So they are based on observations. So usually they are a mix of in situ and satellite observations. And then there are some modelizations that are run based on these observations. And model simulations. So here it's less based on observations. And so for many kind of data sets, you have many ways to access. So the most common way to access is some big open platforms like Copernicus Marine for ocean observations, or if you want to look at the CMIP model simulations, you will go on ESGF. Sometimes you need to look at some production centers platform. So you will need to go on many websites to have each datasets. And sometimes you need to contact the authors, as a dataset might not be published, but sometimes people will be happy to share with you the data they have. And here again, looking in the literature, you'll be able to find what datasets you can use and where to find them, because in the article, you will find the path to data. And one last key important thing here is that the data availability is also inside the dataset. So if we look in particular at in situ observations, you usually have a lack observation in the past and in many places. So if you look at recent observations, chances are high that you have a full coverage for your data, but the more you go in the past, the less data you have. And this also has an impact when you look at reanalysis, because they are based on less data in the past. Okay, so let's apply it to the northeastern Atlantic and adjacencies. And before looking at the surface temperature data, I'll start to try to define what is my region. And here I will use 3 products. So you have the 3 different products. So in first, the gray one is from the WMO. So this is one definition of the northeastern Atlantic. Then you have the blue box here that has been defined for the 8th Ocean State Report, and it is covering all European economic zones. And then you have a third definition that are the large marine ecosystems. So there are many seas around Europe that will look at all together or individually. And when you look at these definitions of regions, you see that so choices had to be made. And in this case, it's more like political and socioeconomic choices that were made rather than physical, linked to physical characteristics. Because especially if you look at the seas or the large marine ecosystems in the north, you'll see that sometimes it has nothing to do with physical properties. Okay, so now that I have defined my region, I will look for SST datasets, and I need them to be covering so the northeastern Atlantic and adjacencies, and also the global ocean, and I need them to be going up to 40 years ago. And here we'll be using 4 observation products. So OSTIA, OISST, ISA-SST, and Odysseia. So you can see here that 3 of them are available on the Copernicus Marine website. And the last one, OISST, you have to go to another production center website. These data, so there are many from satellite observation. They cover the entire globe, and you have different dates. So they all start in the early 80s and end in 2026, or one is one is ending in 2024. So I have my 40 years of observation, and I have some data that are covering the globe. Okay, so now I'm aware of the context. I have my data ready. I downloaded onto data, but I need to check for the robustness. So ideally, each dataset should be provided with some confidence interval, because there are uncertainty in the data, and they have different origins. So, for example, if you look at in situ data, you can have some measurement mistakes that you're aware of. And usually, normally when you're giving, for example, an index for a buoy source, you should say, okay, we measure this temperature, but there is an uncertainty of 0.1 Celsius degree, for example, that we are aware of. So you should also consider this uncertainty. Then, because data are processed before being released, you also have assumptions that are taken by the different production centers. And this is another uncertainty that you have. So this is true for in situ and satellite data. And sometimes the same, for example, satellite data or observations can be used by different production centers to provide some data sets of the same observations. And there you have when you combine them, you have an uncertainty of these assumptions on processes. So as I said, you can have lack in observations that are causing some uncertainty in the reanalysis, because where you're trying to reconstruct a signal with less or no observation, you have less confidence. And lastly, sometimes you have a product that is, for example, an index like the global mean surface temperature. It will be coming from, if you take it from CEMIP, it will be coming from lots of simulations of different models. And if you only get the index, you don't have information on the model uncertainty behind it. And this is the same for analysis. Usually it's computed on 10, 20, 30 members, but in the end, you only get one indicator. But in fact, you have some uncertainty linked to the different simulations that were run. Okay, so like you would expect to have this confidence interval, but usually it's lacking the data sets. And so that's a second reason why you should try to use as much as data sets you can for your study, because that's where you'll be able to see if the data sets agree. Because you cannot know if your data set alone is how much confidence you can have in your data set. And going through literature, you will also be able to identify potential weakness of a data set. So especially, yes, if a data set reanalysis is not good to reconstruct a signal, I don't know, in 1C around the globe, it will be in some, you will find it in publications. And if you were planning to use this data set for this particular region, you can say, okay, maybe I will not use this data set, but keep 3 or 4 other data sets that should perform better. Okay, so we move back to our case study. And here, so the data sets are based on satellite observations and are daily gap-free maps covering the entire globe at various resolutions, starting in 81 or 82. So they all cover the globe for the last 40 years. There's no missing value in time or space. So it's a good point for this choice of data sets. And I also can see that the spatiotemporal resolution exceeds my requirement, because I have a resolution for some data sets that is really fine, and I have daily data. So it's nice to have, but I would not need to be that fine in the resolution. However, there was no confidence interval distributed for some data sets. So it's a lack, but because I have 4 data sets, it's kind of okay, because I will see if the data sets agree in the signals that I obtain. And the literature shows a good trust in the use of these data sets for the global and for the Northeastern Atlantic and adjacent seas. So it's also a good validation to use these data sets. Okay, so now I have checked all available data. I know my context, so I can start to process the data to answer my question. So, and then if I need to apply a specific calculation to my multiple data sets, I have different approach possible. So one is to look at each data set individually. So I will compute the calculation on each data set and then show, for example, multiple index in time or multiple maps, and look at each data set separately. But I might also want to look at like only have one final value. So look at the data sets as an ensemble. And then there are 2 choices. Well, sometimes you don't have the choice. So for example, if your calculation can take as input an average and a confidence interval, then you can do the computation on an ensemble average that you computed at the start, and then do all your calculation on one index plus some variance around it. Otherwise, you can also compute your indicator on all data sets. And then once you have your indicators, you figure out what is the ensemble average and what is the variance, and you will work on it. So if I have some graded data, like in my case, and I need some area averages values, then I will need to compute so area average, but keep in mind that you need to weight your data according to latitude, especially when you have data in the high latitudes near the poles, because it has a lot of impact in your data. Otherwise, you would give too much weight to what is happening near the Greenland or yeah. And finally, so if I want to look at spatial patterns, so it will not be the case today, but I have different data sets, and each data set has a different resolution, different mesh. I have two options. The first one is to interpolate the data on one mesh, but then I will introduce some biases in my data, and in particular around the coast, I will have data that are really, really uncertain. Otherwise, I can decide to interpolate all data on the coarse mesh, and in this doing this, I will be degrading some of the best quality data, but at least I have less uncertainty because I'm not creating some data in between grid cells. Okay, so in this case study, it's quite straightforward. So first, I compute the latitudinal weighted average for each dataset. Then I compute the decadal trend over the 40 years for each dataset. And then I compute an average trend and a 95% confidence interval on my 4 datasets. Okay, so now I have processed all relevant available data for my context. So it's time to analyze and interpret the results. Okay, so here in the context of regionalization, you have to keep in mind that the thinner the regional scale, the higher the potential role of internal variability is in the indicator. And so if you look at something really, really local and at a short time scale, there's a high risk that the signal that you see is masking the long-term signal. And you might see something that is more coming from internal variability processes than a long-term change in your area. And so you might want to, if they are available, to use longer-term datasets because they will give you a broader view of the implications at play. Even if you look only at the last years, what happened in the last years, having this background of what happened in the last 20, 30, 40 years or even longer is a really good tool to be sure of what you're saying. Like you might be able to do some attribution of the changes. And if the region is not too small, then you might want to use some GCM simulations, so from CEMIP, for example, because they will have a really long-term context because they start in 8050. But if your region is really tiny, then it might be that the grid resolution from GCM models is not good enough. So, and again, as I already said a few times in this presentation, you will have to go through the literature because it will help you to understand, okay, what is happening in this region physically, what are the dynamics in the atmosphere, in the ocean, that can me understand what I'm seeing in my figure. And if the literature is not helping me enough, I might be also contacting some specialists to collaborate with them because they will have they will be of high help to help me understand what is happening in a region. Okay, and another thing is that so if I'm using multiple products, as I was recommending in this presentation, so I will have to be careful with the confidence intervals that I obtain. So on one hand, I can have a really small confidence interval compared to the signal. So in this case, I might easily communicate on the signal. I still need to understand what is behind the signal, but at least datasets agree in a signal. But sometimes you have a signal that can be strong but with a really high confidence interval, or you can have a signal that is not really strong, again with a large uncertainty, and you can even have a strong signal but with let's say 1/3 of the data sets that are showing I don't know, cooling, and then 2/3 are showing warming. So you see that there is an uncertainty even in the sign of the change. So in this case, well, we must be really careful with the information that is coming from it. Okay, so I'll move back to the case study, and this is finally the figures that we obtain going through all these steps. And so first, I will look at the northeastern Atlantic and adjacencies. So, oops. Okay, so yeah, so the blue box, or the blue bar, sorry, is coming from the blue box here. The gray one is from the gray box, so similar box, and then the green one is when you put together all the large marine ecosystems. So the first thing we see that there is the warming in the northeastern Atlantic adjacencies is faster than the global trend. So this is shown here with the first three bar plots. It is true for all data sets. So if you look at the uncertainty here, or like the confidence interval, it is quite small as compared to the signal in each region. And you can see that the blue and gray regions that are quite similar show the same change, and the green one is slightly different, coming from the fact that a large area in the North Atlantic is not covered by the LMEs. So there's a strong agreement in between data sets, in between the different regions that I can choose to study this region. So then I can say, okay, so the signal is here. I can trust the signal. Afterwards, I would have to look to try to understand why I have the signals. This is another question. But my question was, how did it warm compared to global warming? So the answer is it was almost twice the rate of the decadal warming in the global ocean. But then the ocean change is not uniform, so I can look at the different large ecosystems. So one thing we might want to look at first is that the three seas that are forming the faster, so the Baltic, Black, and Mediterranean seas, so they are warming really fast, and this can be explained by the fact that are semi-enclosed basins, and also they are not as deep as the open ocean, and this means that the less heat can be exchanged with the open Atlantic Ocean. So that's why they are warming faster. But we can also look at the Faroe Plateau, at the Iberian Coast, and Celtic Biscay Shelf, and they have a slower warming as compared to the big region of interest. But still, it's above the global warming rate. And so this. Oops. Okay, sorry. And this can be also explained in the literature linked to what is happening in the open Atlantic, and especially some fast warming that is linked to pronounced internal variability, like we also see it in the AMV in this region. Okay, so some take-home messages and recommendations. So one big message with regionalization is that the internal variability can have a really strong role when you look at a small region and a small time scale. So if you're trying to assess what is the change linked to climate change, like the to forcing, then you might want to have a wider look in time and in space to be sure that the signal you see is forcing and not internal variability. A second one is that you have to use literature at each step of your study to define the context, to find the data, check them, process them, and analyze and interpret the results. And we also encourage you to use as many data sets as you can, unless you find an explanation of why you should not use one data set. And then it's nice also to, in your study communication, say, okay, we could have used this one, but as mentioned in other papers, it is not relevant for this case study. So these were some more examples of what we did in the Ocean State Report, but I will not cover them today. And thank you very much for your attention.